just going to double check it. We're having a bit of problems with this. Oh, I've just had a message up here that says spotlighted recordings will not be recorded. Okay. Okay, I'm going to continue to record anyway. Anything which I write down on this piece of paper, I will scan in and put on Moodle as well. So yeah, I'll continue anyway. So here we have the test ODE, which is this thing here. Is that large enough for you to see? So this test ODE is simplified because if we were to use a more complicated ODE to test for stability, it means that all of the algebra and all of the analysis we're going to do gets very, very complicated. So we base our stability on this test ODE. Okay, so if I use that test ODE, our Euler method is yn plus h, and our f of ty is simply lambda y. So I'd have lambda yn. Okay, and we got two factors of yn. So if I factorize that, you can see this is our Euler method. Well, what we do is I'm going to say let z equals h lambda. Okay, so h is still the step length, lambda is just some coefficient of y here. Okay. So I'm going to let z equal h lambda. So therefore, my yn plus 1 is equal to 1 plus z yn. Okay, so I've got this is my ODE method. So I'm using Euler, and this is just the method applied to solve the test ODE. So we have our updated solution is our current solution multiplied by 1 plus z. Now this 1 plus z is known as the stability function. Okay, so this is what we call Rz. So a stability function is Rz. Right. Now, the reason we've written it in this form is because, remember, we're only approximating the solution, so we have errors. So we have an error at each step. We have an error, and that's attributed to the fact that we truncated the Taylor series. So the error at each step will also be multiplied by 1 plus z. So we want our errors to be bounded. So if we want a stable method, so for stability, the modulus of our stability function has to be less than or equal to 1. Okay, so we got to ensure that for any method, the modulus has got to be less than or equal to 1. So this stability function is based upon applying our method to that test ODE there. Okay. I'm just going to switch back to the notes. Actually, I'm going to bring the notes in. I've got the hard copy here. Okay, for the explicit Runge-Kutta method, and on page 43 of the notes, let's see, I've got equation 4.5. This is the stability function of an explicit Runge-Kutta method. So they're different. So implicit and explicit methods, they are different. So for an explicit method, this is our stability function. So you can see, if I just take one of the, let's take the second order term here. So we have B transpose, so this is our vector of B values, transposed, multiplied by our A matrix, multiplied by a vector E. Now that vector E is simply a vector of 1s. And we assume that B and E are column vectors, so that means B transpose is a row vector. And you'll notice that the power of A is 1 less than the power of Z. Okay, so we have this. So each coefficient of Z is B transpose multiplied by A to the power K minus 1 multiplied by E. Okay, so that's what we're going to be looking at. So I'm going to be looking at the stability function of an ERK method. Okay, right, so just make sure I've got that there. Okay, so this is for ERK method. And I just remind myself what the stability function is. It's 1 plus a summation k equals 0 to infinity of B transpose times A to the power k minus 1. Oh, sorry, that should be, sorry, e to k times E, and it's zk plus 1. Okay. Right, so what I'm going to do is I'm going to determine the stability function for a three-stage explicit Runge-Kutta method. So this is an additional example. You might want to follow along with this. I'll be scanning these scribbles and putting them on Moodle as well. So this is a three-stage method, and that's our butcher tableau. So in this case, our A matrix. Is the screen really blurred? Is it? Don't know whether there's is it an automatic focus? Right. So it might be Wi-Fi connection issues. Okay, so that's our A matrix. Okay, we also got our B vector, which, remember, we assume it's a column vector. And our E vector is simply a column vector of ones, same number of stages as we have. Okay, so if I want the coefficient of Z, okay, we have B transpose multiplied by E. Okay, so B transpose is going to be a row vector. Same Wi-Fi issues, are there? Keeps going blurry, so it might be an autofocus thing on this screen. So that's probably what I'm moving my hand in the way. Okay, so we have this matrix multiplication, so that's just adding these up. So 1/6 plus 2/3 plus 1/6, so that's going to be 1. So I know, but my coefficient of Z in my stability function is going to be 1. So what about coefficient of Z squared? So what it is, it's B transpose times A to the power k minus 1. So in this case, k is 2, so A is the power 1. Move that up slightly. And that's multiplied by E. So again, 1/6, 2/3, 1/6. Okay, now I'm going to write the A matrix down. Thankfully, most of the A matrix are zeros, so it doesn't mean that we're doing a massive amount of multiplication. And it's multiplied by E. Okay, so if I multiply these two together, so I've got 1/3 and a 3/3, so that's going to give me a 1/3. So I've got 0 plus 1/3 minus a 6th. So that's going to be, sorry, I'll do that again. Actually, I'll do these. I'll do the second two matrices first. Okay, so I've got 0 there, got all the zeros, got 1/2, and I've got -1 plus 2, so that's going to be 1. Okay, so if I multiply these together, I've got 0 plus a 1/3 plus a 1/6. Is that correct? Have I made an error here? Should be a 1/2. 0 plus 1/3, so that's 2/6, that's 1/3, plus a 6, which is, oh yeah, 3/2. Sorry, I can't do fractions. Sorry about that. Okay, so that's the coefficient of Z squared is 1/2. Okay, so the coefficient of Z cubed. Okay, so this B transpose A, now we've got squared because it's 1 less than the power of Z. Okay, and then E again. So this time we do have a square of a 3 by 3 matrix, but most of those values are 0, so it makes it a little bit easier. To be a 0, 0. Okay, so I'm going to leave B transpose for now. And I'm going to multiply these two together. So 0 is on the first row, 0 there, that's because 0 is on the second row. The only non-zero element is going to be 1 there. Okay, so oh, can you see that? Sorry about that. If I multiply these together, 0, 0, 1/6. Okay, if I was to continue, this would just be all zeros, because if I multiply this by that there, I'll just get all zeros. So I'm going to stop there. Okay, so what we can say is, but our stability function, Rz, can you see that? Our stability function, Rz, is 1. I'm just going to scroll back. So that's that 1 there. And then we have the coefficient of Z, which was 1. So we've got 1 times Z. Coefficient of Z squared was 1/2. And a coefficient of Z cubed, so Z cubed was 1/6, not 1/3. Okay, so that's what we call the stability function for this explicit Runge-Kutta method. Now, the test equation was so the test equation, if you remember, was y dash equals lambda y, and that has a solution e to the lambda t. Are you able to see that there? I don't know whether it's gone off my screen, so I don't know whether it's. I'll leave that up there. Okay, so this test equation had the solution y equals e to the lambda t. So that means our solution is an exponential function. So that means our errors will also be the exponential function. Now, e to the z, the series expansion, is 1 plus z plus 1/2 z squared plus 6z cubed plus a 24th z to the power 4, etc. So what we do is we compare our stability function to the series expansion of e to the z, and where it's the maximum order, which they both agree, is the order of our Runge-Kutta method. So you can see here, this agrees up to 3rd order because we just got zeros here. So this is the 3rd order explicit Runge-Kutta method. Okay, so just going to share my screen for a sec. So this is the coursework. So you can see here, for 3 marks, once you've derived your ERK method, you then need to determine the stability function, and that's kind of similar to what we've just done. Okay, are there any sort of questions about that? Are you able to see what I'm doing? Is it still blurry, or is it? Are you able to see it? Okay, I'll always assume no news is good news. So if I hear silence, that's fine. Okay, so that's for explicit methods. Now for implicit methods, slightly more involved. Okay, so I'm just going to bring in my notes here, and this is on page 47. And we have, for implicit methods, we use this to determine our stability function. This is equation 4.7 on page 47. Okay, so you can see we have we'll have some function on the numerator and some function on the denominator. And I is the identity matrix. Now this EB transpose, this is a square matrix with the elements of B on the main diagonal. Okay, so what I'm going to do is have a look at the stability function for an implicit Runge-Kutta method. Again, this is an additional example, and this will be similar to what you need to do in the assignment. Okay, so I'm going to. Oh, I can't. Just trying to see where are we on the camera? There we go. Right, so this is for an implicit method, IRK. Okay, and the butcher tableau we're going to be looking at is one which I prepared earlier. Okay, so there's our butcher tableau. Are you able to see that? Okay. Yeah, I assume you can. Okay, so our stability function for an implicit method is, I'm just going to write it down. This is given in the notes as well. Is it EBT or, yeah, it's EBT, isn't it? EBT all over determinant I minus ZA. Okay, so in this case, we have our A matrix is a half 0 minus a half 2, and our EBT. Okay, so this is going to be a 2 by 2, so we need it to be the same size as A. So we've got B1 is minus a half, and B2 is 3 over 2. Okay, so I'm going to plug them into that. Let's see what we get. So this one, implicit methods are slightly more involved, as I've mentioned. Okay, there's our 2 by 2 identity minus Z, and we've got a 2 by 2 A matrix minus our EBT. Okay. Okay, and on the bottom, we've got the determinant. Again, we've got our 2 by 2 identity, but minus Z times our A matrix. Okay, so there you can see we've got a couple of determinants calculate. Okay, so let's see what we got. So here we've got half minus minus a half, so that's 1. But then that's multiplied by minus Z, so that's 1 minus Z. Here we've got 0 minus 0, which is 0, and 0, so that's going to be 0. Here we've got minus a half multiplied by minus Z, so that's a half Z. And here we got 2 minus 3 over 2, which is 1 half, times minus Z, so that's minus 1 half Z. All over, and determinant on the bottom. Oops, not too many brackets. So this one's easier. It's 1 minus a half Z, 0, half Z, and where am I? 1 minus 2Z. Okay, so these are easy 2 by 2 determinants. So I've got 1 minus a half minus 1 is minus 3 over 2Z. And so we've got plus a half Z squared on the top. And on the bottom, we've got 1 minus 5 over 2Z plus 1, plus Z squared. Okay, so that's our stability function for the implicit Runge-Kutta method. Now, with implicit methods, a really desirable property of them is that they're astable. Now, astable methods essentially means we can use any value for our step length. Okay, so it's not bounded. So the step length H, there's no constraint on it based on stability. I'm just going to bring in the notes again. Okay, so you can see here we've got notes. This is page 47. So an astable method is there's no limit placed on the value of H. Okay, so to determine whether a method is astable, okay, if we have our stability function is some polynomial P of Z, over another polynomial q in terms of z. Okay, so we've just seen in our example, okay, we have on the top we have our p of z, and on the bottom we have our q of z. Okay, so p and z, q of z. Okay, so we got by this theorem down here. You can see that. I don't know whether you can actually see that. Okay, so this theorem here, we've got two criteria that needs to be satisfied. The first is the roots of our denominator has got to have positive real parts. And the second, if we define this polynomial function here, p and q are there, if this function is always greater than or equal to 0 for any value y, which is a real number, if both of these two are satisfied, we have an astable method, which is good news because then there's no bounds on the step length we can use. So the easiest, well, the first thing we're going to do is look at the roots of qz. Okay, so the roots of qz. So what I'm looking for is solution to that equation. Okay, so obviously we use the quadratic formula. So we've got minus b plus or minus root. B squared is going to be 25 over 4 minus 4. So that's 25 over 4 minus 4. So that's going to be 25 minus 16 is 9. So it's going to be root of 9 over 4. All over 2a, which is 2. 9 over 4 comes out quite nicely because that's 3 over 2. All over divided by 2. Okay, so we've got 2.5 plus 1.5 divided by 2. So that's 4 over 2, it's 2. And we've got 2.5 minus 1.5, which should be 1 divided by 2, which is 1/2. Okay, so the roots of qz are both have real parts greater than or equal to 0. Okay, so more often than not, you have complex numbers as your roots, but we're only really interested in the real part. So in this case, the roots of qz both have real parts, which are positive. So that's that first criteria dealt with. So then we have to move on to the second criteria. Okay, and I just write down that function EY. So EY was Q, IY, Q, minus IY, minus P, IY, P, minus IY. Okay, so that's what we're looking at. And just to remind ourselves, I write down what QZ was. QZ was, it's over the other side of the page, but it's 1 minus 5 over 2z plus z squared. And pz is 1 minus 3 over 2 z plus 1/2 z squared. Okay, so I've got to build this function EY. It's quite involved. It's kind of got four main parts to it. So that's what we're going to be looking at now. Okay, so EY. So start we've got QIY. Okay, so we've got 1 minus 5 over 2 IY. So instead of Z, I've got IY. Now here I've got Z squared. So if I square IY, I get minus Y squared. That's going to be minus Y squared. And do the same, but this time I've got minus IY. So it's going to be 1 plus 5 over 2 IY minus Y squared. Okay, so that's the first two done. So now I've got PIY. So again, we're using the P1 now. So I've got 1 minus 3 over 2 IY and 1/2 Z squared. Well, if Z is IY, Z squared is minus Y squared. So I've got minus 1/2 Y squared. And for for this, for the last one, it's very similar, except for this sign is different. Okay, so we've got a couple of 3-element brackets to expand out. So you can do this a number of ways. I just prefer to take it slow and do it methodically. So I'm just going to multiply every term in this bracket by every term in that bracket. So we're going to end up with 9 terms each in each one, but at least it's less liable to make mistakes. So that's that multiplied by 1. So now I'm going to multiply all these by minus 5 over 2 IY. Going to have minus 5 over 2 IY. So now I'm going to have minus 5 over 2 IY times plus 5 over 2 IY. So that's going to give that's going to give me minus 25 over 4 y squared times I squared. Well, obviously I squared is minus 1. It's going to be plus 25 over 4 y squared. And 5 over 2 IY times y squared, that's going to give me plus 5 over 2 IY cubed. Okay. Finally, going to multiply everything in that bracket by minus y squared. So minus y squared minus 5 over 2 IY cubed and plus y to the power 4. Okay, so that's that first bracket done. What you'll notice is our i's. I'm missing a half. Yeah, thank you. Thanks for that, Georgia. Okay, so what you'll notice, I've got 5 over 2 IY minus 5 over 2. So the i's, the imaginary numbers can't actually cancel out. So they'll cancel out on the next step. Okay, so now I'm going to expand this one out. Same way. I mean, it's nothing too tricky. It's just a bit long-winded. And then we've got minus 3 over 2 IY plus 9 over 4 y squared. And then we're going to have plus 3 over 4. So just double check that. So yeah, plus 3 over 4 IY cubed. And then finally, minus half y squared minus 3 over 4 IY cubed and plus 1/4 y to the power 4. Okay, so it looks ghastly at the moment. So it looks a bit horrible, but like I said, a lot of things cancel out. So if we look at the first, okay, those cancel out. So and we've got another one's cancelling out here. So our first bracket is 1. Y squared, so we've got minus y squared there. But we've got plus 25 over 4. So that's minus 2 plus 25 over 4. So that's minus 8 plus 25 over 4, which is 17 over 4. So that's 17 over 4 y squared plus y to the power 4. The second bracket, again, can start cancelling out imaginary numbers, the imaginary terms. So we have 1 minus y minus half y squared minus half y squared, but plus 9 over 4. So it's going to be minus 1/4. Sorry, minus 1 plus 9 over 4. So what we got? We got brain's gone to sleep. It's got minus 4 over 4 plus 9 over 4 is plus 5 over 4 y squared plus 1/4 y to the power 4. Okay, so 1 minus 1 is 0. 17 over 4 minus 5 over 4 will be 12 over 4, so that's 3y squared. Y to the power 4 minus 1/4 y to the power 4 is going to be 3/4 y to the power 4. Okay, so after all that gubbins, EY comes down to 3y squared plus 3 over 4. Now, here, because we have even powers, our E y is always going to be greater than 0 for all y is a real number. Okay, so that second criteria is satisfied. So if I just go back, so we showed that the roots of qz, or the roots of the denominator of our stability function, had positive real parts, and we calculated what Ey was, and is always positive, or greater than or equal to 0. So therefore, this is an astable method. Yeah. Okay. So we can say that that is an astable method. Okay. Right. Did that all sort of make sense? Were you able to follow what I was doing there? Most of it was just algebra. What I would say is in the lecture notes, you see, I mean, we've got, if I just bring it in here, I just used this, but the preceding, you can see where this comes from. If we have a look at the preceding, where that's derived from, and also for the explicit random cutter method, you can see where that comes from. So I do recommend having a read of the notes, and also follow the examples. And we'll be working through these worked examples in the webinar tomorrow as well. Right. So if I just go back to the assessment. So now for part B, you should be able to do all of this. So we've covered derivation of ERK method, stability function for ERK, applying an ERK method, derivation of an IRK method. We've just done the stability function and test for whether it's astable, and we've done applying an IRK method as well. Okay. The second part of part B, okay, this is what we call a numerical experimentation. Okay, so I think I mentioned this in the past. So you're asked to find what is the target rate for infection. So beta target, I've called it here. That ensures that no more than 2 million persons are infected. Now, how you do that is up to you. Okay, there's no right or wrong way to do that. I don't have in my mind a way which you should do it. I mean, there's different approaches. Okay, so this is more like once you've got the model working, you're going to use the model to actually try and find out what's our target infection rate. Okay, so as you could probably tell, this question here is sort of influenced by recent events as well. Right. Okay, right. Okay, are there any questions about stability? Are you there? Okay. Are there any questions about the assignment? I mean, are you happy about the assignment? You know, can you sort of got everything you need to sort of get going and complete it? Again, I'll take silence as good news. There was one question which was posed by a student in the earlier session, and it's on the assignment on 4 part B. Okay, I have said using pen and paper determine the stability function. What I mean by that is don't just use MATLAB. Okay, you can use MATLAB and in 30 seconds you can get the stability function. So I want to see full working. So similar to what we've done here. So use pen and paper for your rough work, and then I still want you to type it up. So it's not like you hand in your handwritten work. So with using pen and paper essentially means not using MATLAB for that part. Okay, so I'm going to stop the recording there. I think I did have a message come up, but